Bismillahirrahmanirrahim. Okay, good night everyone. My voice clear or not? My voice. Please comment. My voice. Please comment if my voice is clear. Can you listen to me? Clear? Okay, so in this session, I would like to continue stiffness method. Okay, this session we discuss work example beam analysis indeterminate beam. Okay, so let's look at the question. Okay, basically for stiffness method, we will use the same procedure for thrust analysis, beam analysis as well as frame analysis. Anyway, we have little difference, okay, between beam and thrust. Okay, so in terms of degree of freedom, if thrust we have to consider the degree of freedom per node in x and y direction, because there is no moment, there is no rotation in thrust. In beam, we still have to consider 2 degree of freedom, but this time we have to consider degree of freedom in y direction and y component and z component. Y means for Q and D. For Q and D, we represent the vertical force and vertical displacement, and Z for forces, and for force and displacement will be for moment and rotation. We don't have to count in x component. We don't have to count because axial, there is no axial force. Axial force normally in beam we will always get 0 for the horizontal force, and due to that the axial deformation can be neglected. Okay, so we only have to count 2. Okay, so another thing difference between beam and thrust is, okay, if for thrust we use stiffness equation. We use stiffness equation Q is equal to KD. But in beam analysis, beam and frame as well, in beam and frame, for the stiffness equation, we have to use Q is equal to KD plus Q naught. Okay, so in thrust we have Q is equal to KD, where Q is nodal forces, D is nodal displacement, K is structure stiffness matrix, and now in beam we have to consider Q naught. So what is Q naught? Q naught is called as equivalent nodal forces. That will cover this thing and this thing. Okay, whenever the member or element is subjected to load, okay, there is a UDL along the member and point load on the member at the center or at anywhere on the member, not at joint. So we have to consider this as Q naught, equivalent nodal forces. Okay, so we have Q nodal forces. Nodal forces means whatever force that is subjected directly at nodes. Subjected directly at nodes, so we call it as nodal forces. We have Q naught. Okay, Q naught is equivalent nodal forces. Equivalent nodal forces is come from equivalent element nodal forces. Q1 naught plus Q2 naught. Q2 K1 naught plus Q2 naught. Then we will have Q naught, Q capital. Okay, as usual, small letter means for element, small letter means for element, and capital letter means for the whole, Okay, and as usual, we have K is the structure, stiffness, matrix, and we have D. D is equal to nodal displacement. Nodal displacement means displacement uh, that is located at nodes in y and z direction. So degree of freedom for beam, we have to count in these two direction. Okay, this is y direction and z direction. Y and z direction. So we have to always follow this direction. We cannot change the direction. We cannot change the direction because this is the direction that is used in deriving the equation, the stiffness matrix, Okay, I want to open the appendix. Okay. Okay, this is for beam. Okay, beam has 2 degree of freedom in y and in z direction. So we focus on the global coordinate system. Okay, we focus on the global coordinate system, and beam has actually has uh, same global and local beam. Only beam has same local and global. That is why we will find that the formula for local and global is the same. Okay, anyway, we just need to refer to the global coordinate system. Okay, as usual, one beam, one element consists of 2 nodes. This is near, the arrow is always going to the right direction. The arrow is always going towards right direction. So the arrow move towards far end. So this will be far end. This is far, and this is near. Far, near, and far. Near to far. Okay. And at each node, there are 2 degree of freedom. There are 2 degree of freedom in y direction and in z direction. Y and Z direction for near end, and Y and Z direction for far end. Okay, so in total we will produce 4 by 4 matrix. It is 4 by 4 matrix. Okay, and we have to label as previous. Okay, as what we have done in class, we have to label start from near. This one is YZ, near YZ, far YZ. If we follow follow this, if we follow this, it is 1, 2, 3, 4. Okay, anyway, it always depending on how we label degree of freedom according to unconstrained and constrained system. Okay, so this is the formula. So inside this, okay, we will find that the formula we have to calculate in terms of EI. EI will be put outside the bracket as usual. Okay, and there are actually 4 values. Okay, inside this, it is 12 over L cube, and then we have 6 over L square, and then we also have 4 divided by L, and last value will be 2 divided by L. Okay, means that there are 4 values inside this matrix. Okay, so we will follow, we will use this formula whenever we want to calculate the stiffness matrix for each element in the beam. Okay, anyway, in terms of labeling degree of freedom, labeling the degree of freedom due to unconstrained and constrained system, we have to be careful. Okay, let's go back to this one. Okay, this is just like conventional type of beam where we can also analyze this using flexibility method. If in flexibility method this beam has 5 unknown reaction, 5 unknown reaction. Okay, there will be 2 redundant if we calculate this using flexibility method. But using stiffness method, we will determine the displacement first. Displacement, then only we calculate the unknown reaction. Okay, so consider the beam in figure below. The beam is a continuous beam with 3 support. There are fixed at A, B and C roller. EI is assumed to be constant throughout the beam. Calculate rotation at B and C, and then draw bending moment diagram for the beam. Okay, take modulus of elasticity E equal to 200 GPa, and inertia. The moment of inertia is 500 exponent 6 millimeter 4. Okay, so most important, still we have to follow what we have done in thrust analysis. Okay, where the first step is we have to label degree of freedom. We have to label degree of freedom, and I want everyone to draw it separately between unconstrained and constrained. Unconstrained and constrained. Okay, so how to do this? Okay, let's say I redraw the diagram. Okay, this is the diagram. Okay, just look at this diagram conventionally. UDL, point load, roller. Okay, indeterminate beam. This is indeterminate beam. Okay, looking at the support, there are 5 unknown reaction. Looking at the support, we know that there are 5 unknown reaction. This is conventional way how we look at this beam. Okay, we have this, and this. Okay, this is conventional. The way we look at this beam conventionally, there are 5 unknown reaction. Okay, these 5 unknown reaction we want to transform into two beam, one for one for unconstrained and one for constrained. Okay, so I want to divide this beam into two. Okay, one is for unconstrained degree of freedom system, and another one is for constrained degree of freedom. Just do like what we have done previously. Okay, so okay, one important thing is this one, since there is no Cx Cy in the formula. In thrust analysis, in the formula, it has Cx and Cy. Cx and Cy, we have to have the coordinate in order to determine Cx and Cy. And because beam, in the formula, there is no Cx, there is no Cy mentioned. Means that we don't have to label coordinate for beam. Okay, so means that the K, the stiffness for beam will be depending on the length of the beam and also EI. So that is why and arrow also understood, yeah. The arrow is always a move towards far and a move towards right direction. So in this diagram, we don't have to put we don't have to put coordinate. We don't have to put arrow. Okay, this one is understood. The arrow is always going towards right direction. Okay, so we don't have to put the arrow, and we don't have to put coordinate as well. So we don't have to put coordinate, and we don't have to put arrow. So this is actually the member, the nodes, not A, not B, not C, or not 1, 2, 3. A, B, C also can be used. And A to B is element number 1. B to C is element number 2. So there are two elements. So back to this. Okay, so the easiest way to identify degree of freedom for unconstrained and constrained is by looking at the beam conventionally like this. So draw the free body diagram. This is the free body diagram, right? This is the free body diagram. Okay, like what we have always done previously. Okay, there are three unknown reaction at fixed support. There is one at roller. So total is 5 unknown reaction. Then we just need to sketch unconstrained and constrained. So one line for unconstrained beam, one line for constrained beam. We label the nodes. A, B, and C. A, B, and C. We just need to label the nodes. Okay. Now, always remember that under constraint system, there are unknown reaction. QU. Under constraint system, there are unknown reaction, and under unconstrained system, okay, there are unknown displacement. Okay, so this is unknown displacement, this is unknown reaction. Okay, so looking back at the 5 unknown reaction, always remember when we want to transform into the free body diagram, okay, here, due to constraint degree of freedom, we do not have to count the horizontal reaction at A. We do not have to count the horizontal reaction at A, because the degree of freedom that we need to consider is only in Y direction and in Z direction. So at A we just need to count 2. At A we just need to count 2 degree of freedom. So we put here 2 degree of freedom. 1, 1, 1, 2. Okay, we only count 2 and we have to put under constraint system, constraint degree of freedom system. And look at B. Okay, B 1 in Y direction and C 1 in Y direction. So we put 1 in Y direction at B Y component and another one at C. Okay, means that there are 4 degree of freedom under constraint degree of freedom system. There are 4. Okay, always remember that we have to have two each nodes. 2 each nodes means that we have to complete, each node must have 2. Okay, so we don't have to put DOF at A because at A, okay, already has 2 in constraint system. So under unconstrained degree of freedom, so at constraint it only has 1 in Y component, so we have to have another 1, okay, in Z component under unconstrained. So here we have to put this, okay, in Z component at B, so that at B now complete 2 degree of freedom in Y and Z component, and another one Z will be put at C. Okay, so we have, okay, due to this we have two unknown displacement. We have two from this we will have two unknown displacement. We have 2 here, unknown displacement, and we have 4 unknown reaction. We label as 4 QU, and this is 2 DU. Okay, so means that the DU will be D1 and D2. D1 and D2 means that this is the first outcome. This is the first outcome. When we solve for the unknown displacement, when we solve stiffness equation, we will solve for D1 and D2. Okay, and then we have four unknown reaction. So 1 and 2 will be put here, 1 and 2, and we will continue to label. Okay, you can start at C, you can also start at A, doesn't matter. Okay, this is 3, 4, 5, 6. Okay, 3, 4, 5, 6. The reason why I put 3 in Y component, 4 in Z component, because whenever we want to label the element stiffness matrix, we will call it as near YZ. Near YZ means 3, 4. Okay, it doesn't matter. You can also put in the other way around. You can also put 3 for Z, 4 for Y component. Okay, so it's up to you. You can also start 3 at C. Okay, it's up to you. Okay, so based on this, so means that the label for the unknown reaction, will be Q3, Q4, Q5, and Q6. So these 4 will be the unknown reaction. Okay, let's understand more about this. Because we want to always look at Q and D from 1 to 6. we have to be able to imagine. Okay, means the physical meaning. What is Q1? What is Q2? What is Q6? What is D1 until D6? So we have to look at this back again. Okay, refer back to this. Okay, AB, this AB, okay, this is A, B, C. Okay, back to the question, 1 kilonewton per meter and 10. Okay, this is 10 kilonewton, this is 1 kilonewton per meter. Okay, okay, now based on our understanding, when we first learn about deflection of beam, okay, if we want to draw the deflected shape of this beam, okay, how it will look like, deflected shape of this beam. Okay, don't forget we have fixed at A, and there is no rotation, there is no rotation at fixed, there is no vertical movement at fixed. At roller has rotation but no movement. Okay, so based on that understanding, we have to draw the deflected shape of the beam. Okay, this is just to visual. Okay, to visual the deflection, so that we can relate with degree of freedom that we have labeled from 1 to 6. Okay, this is not compulsory. Okay, this is just to visualize. Okay, so due to AB has UDL. AB has UDL, and A is fixed, B is roller. So what happened to the beam? The beam will deflect like this. Okay, beam AB will deflect like this. Okay, A to B will be deflect like this. So we cannot draw the deflected shape start from A because of the support. So in order to understand this, we have to understand the fixed end support. So at fixed end there is no rotation. At fixed end there is no rotation, means rotation at A equal to 0. There is no rotation and there is no vertical movement. Delta at A is equal to 0. Delta at A is equal to 0. Again, we don't have to count in horizontal component. Because the value is always 0. Okay, so that is why when we draw the deflected shape, we have to draw somewhere here. Okay, the effective length is about 0.7 LE or 0.75 LE. So you have learned about this under buckling. Okay, in CES 424. Okay, however, for BC, since B is roller, C is roller, or pin also have the same condition. So due to this, okay, we will draw deflected shape of this beam BC like this. Okay, so what does it mean? At B, theta at B. Theta at B means this tangent. This is theta at B. So we can see clearly that there is a rotation. Okay, there is a value of rotation. Okay, theta B. This theta B is not equal to 0. Because we can see from the diagram, okay, from the tangent line of the curve, okay, it will representing theta at B, rotation at B. Anyway, for the vertical component delta B, because of the support there is no movement. Okay, so delta B is equal to 0. Okay, and now at C again, the tangent line is theta at C. So this theta at C is not equal to 0. Anyway, delta, vertical component delta at C is equal to 0 because there is no vertical movement because of the roller support. Okay, so what we can conclude is, so when we draw a diagram, the deflected shape of the beam, we can conclude that, okay, there are two displacement which the value is not equal to 0. It is belong to theta B and theta C. And there are 4 zero displacement. There are 4 position which the value equivalent to 0. Okay, theta A is equal to 0. Delta A is also equal to 0. Delta B is equal to 0. Delta C is equal to 0. So if we compare this, to this label, okay, this label, what we can find is, okay, we have D3, D4, D5, D6. Okay, and D4, based on the label that we use, D4 is actually, okay, displacement, Z displacement, it is rotation at A. So D4 is actually rotation at A. D3 is theta at A. D3 is theta at A. Okay, D5, D6. Okay, D5 is theta B. D5 is theta B and D6 is theta C. Okay, so D3 equal to 0. It is actually equal to delta at A. D4 is 0 and this is theta at A. And D5 is 0, this is equal to delta at B, and D6 equal to 0, this is equal to delta at C. Anyway, labeling this, all these label will be depending on how you label the degree of freedom. Okay, based on your labeling. Okay, so for the unconstrained system, at position 1, D1 is rotation, D2 is rotation, and D2 actually refers to, it is in Z component, it is unknown. So there are two unknown, this is unknown and this is also unknown. Theta at B is not equal to 0. Theta at C is not equal to 0. So D1, based on the label that I use, D1 is actually theta at B and D2 is theta at C. Okay, and at same position Q1 and Q2, okay, we have to put value because it is unknown versus known. Unknown versus known, okay, if D is unknown, Q must be known. Okay, means that Q is rotation at position B and Q1 is no, not rotation. Q1 is moment at position B and Q2 is moment at position C. Okay, Q1 is moment at position B and Q2 is moment at position C. Okay, okay, means that look at position B and at position C and find the moment value if it is given in the question. Okay, back to the question. There is no moment at B, there is no moment at C. So, what does it mean? What does it mean? Looking at the diagram, there is no moment at B and no moment at C. Means that Q1 and Q2 is equal to, what is the value of Q1 and Q2? Can you write something in the chat box? Q1 and Q2. Q1 is moment at B. Q2 is moment at C. Okay. Since there is no moment subjected at B and at C, so Q1 is equal to 0, Q2 is equal to 0. Okay, 0. Okay, it will have value if we have moment. For example, let's say if moment is given here, for example 100 kilonewton meter. Okay, means that Q1 will be equal to 100. Okay, if only moment is given in the question. If not, the moment is equal to 0. Okay, always remember between Q and D, it is known versus unknown. It is known versus unknown. If D is unknown, Q must be known. Okay, means that we have to put the value, find the value from the main diagram. Okay, we go back to this. Okay. So step number 1, we have to label degree of freedom according to unconstrained and constrained. Okay, always remember we label unconstrained first because unknown displacement will be determined first. Okay. So then only we followed by constraint system. So we label like this. Okay. So step number two, we just need to substitute into the formula. Substitute the L value into the formula because EI will be remain constant here. So we just need to find 4 values. Okay, it is 12 EI over L. It is 6 EI over L, 12 over L cube, 12 over L cube, 6 over L square, 4 over L, and 2 over L. Okay, we just need to use this formula and we establish the element stiffness matrix for member AB. K1 is for member A, B. K1 is for member A, B. Okay, so what most important, we have to label the diagram, the K correctly. We have to label the K correctly. So based on the label here, okay, so the element number one, we should label start from near. Arrow is always move towards right direction. So near will be A, far will be B. So we have the label as 3 4 3 4 YZ 5 1 YZ. Okay, this is how we label. 3, 4, 5, 1. YZ, YZ. Okay? 3, 4, 5, 1. YZ, YZ. Near to far. Near to far. Okay, same goes to BC or element 2. Element 2 we have. Element 2 we have. YZ, YZ near to far. YZ is 5, 1. 5, 1. Okay, far YZ is 6, 2. 6, 2. So the label, the K label will be 5162. 5162. Okay, so this is K1. K1. Okay, EI remain constant. EI remain constant. So we label as 3451, 3451. This is for K1, and then we will do the same for element number 2. Element number 2, the label will be, for element number 2, the label will be 5162. 5162. Okay, so anyway, this label will be always refer to how you label the diagram. It depends on you. Okay, so this is 5162. Then we have to combine this K1 and K2, K1 and K2 to produce the structure stiffness matrix. To produce the structure stiffness matrix. So the next step, step number 3, okay, we have K1 and K2. Okay, so K1, the label is 3451, 3451. And for K2, we have 5162, 5162. Okay, so for the structure stiffness matrix, we have to find the value in 6 by 6 matrix. So all the degree of freedom label is actually based on the position in the structure stiffness matrix. So we have to do it one by one, like what we have done in truss. Okay. So we have to do it one by one. 1 1 1 1. So this is 1 1 plus this plus this. Okay. So we get this one, and then we continue 1 2. So there is no 1 2 in K1. We only have 1 2 in K2. So this is 1 2 to 1 is the same. Okay, and then 1 3. So this is 1 3 0.074. We get 1 4. So you have to do it one by one as we have done previously. One by one. Okay, 1 4. 1 4 4 1. The same. 0.022. 1 4. Then 1 5. 1 5. Okay, exists in K1 and also K2. 5 1. So 5 1 1 5 is the same, and 5 1 1 5 is the same. So we have to plus these two. So we get this. Okay, and then 1 6. 1 6. 1 6 is negative 0.667. So we have to continue. We have to continue until the end, until we write 6 6 value. at 6 position, the value for 6 position. So this is called as structure stiffness matrix. Okay, this K, capital K is structure stiffness matrix. Structure stiffness matrix. Okay, now, okay, nodal forces and nodal displacement. We just need to summarize what we have do it previously. We substitute into matrix form. Q in matrix form is called as nodal forces. D is nodal displacement. So the information that we have written, okay, we have written here. Okay, so we transform into matrix form. So we get like this. So Q, okay, so this is the boundary between unconstrained and constrained, the boundary. Okay, it is known versus unknown. This is known. Known. QK is known, QU is unknown. Known versus unknown. Okay, same goes to DU unknown, DK known. Known versus unknown. Okay, so next thing is the step number 3. We want to highlight on the Q naught, which is called as equivalent nodal forces. So previously we have Q that is called as nodal forces. Now Q naught is equivalent nodal forces. Okay, it is equivalent. What does it mean? Equivalent. Okay, what does it mean? Okay, we have to remember the stiffness method. We only analyze displacement and forces at nodes. Means that if the member has loading, is subjected to loads, the member, we have to distribute to nodes. Okay, member cannot carry loads, so we have to distribute it to the nodes. Okay, for example, if we have point load, this P is not subjected at nodes. If P is subjected at node, it is Q. But this time P is not subjected at nodes. So when P is subjected on the member, whether it is at the center or it is anywhere on the member, what we need to do is we have to distribute to the nodes. And we distribute it equivalently. So for doing that, we have to assume that both ends are fixed, A and B are fixed. Then we will have the vertical reaction as well as the moment at both fixed ends. Okay, the formula is anyway given in the appendix. However, for point load like this as well as UDL, the formula is quite straightforward. Okay, so this is called as fixed end reaction. Under the appendix, fixed end reaction. So let's look at the appendix back. Okay, under appendix page 3, where is the page 3? Okay, not inside, doesn't matter. Okay, so when we want to calculate, okay, Q naught, it is actually we just need to understand that we will have Q naught, we will have Q naught whenever we have loading like this. UDL UDL is the load that is subjected along the member, not at nodes. So we have to distribute it to the nodes, and we have to distribute it equivalently. And for BC, point load, 10 kilonewton point load is subjected also not at nodes but at the center. At the center means on the member. So it must be distributed, to B and to C equivalently. Okay, so in order to do that, we have to understand about fixed end reaction. So all this is called as fixed end reaction. Fixed end reaction. Okay, so these are all the formula given actually. Okay, and by looking at this diagram, this P must be balanced. This P must be balanced because this P is subjected at the center. Okay, of course there is a formula when P is not subjected at the center, but we focus on this example where P is located at the center. So since we have to assume that both ends are fixed, so there will be reaction at A, reaction at B. It is vertical reaction, vertical reaction as well as moment. Okay, for the vertical reaction, we have to balance the P, means that we will have P over 2 here and P over 2 at A, P over 2 at B, so that the system is in equilibrium. The system is in equilibrium. Total Fy is equal to 0 when P over 2 plus P over 2 balance with P. Okay, that is fixed end reaction. So same goes to the moment. Fixed has moment value, and due to P that is subjected at the center, we will have moment, fixed and moment. This is fixed and moment, okay, at A, B, and this is fixed and moment at B. Okay, and the fixed end moment is acting. Okay, the fixed end moment, remember that the system must be in equilibrium. The system must be in equilibrium. That is why when the system must be in equilibrium, this is P over 2, this is P over 2, so that this P, we get minus P over 2, minus P over 2, we get 0. Okay, so that is the formula. So for the moment, since fixed end moment is the behavior moment, the moment is always behave in this direction, these two direction, because due to P, this beam will bend. Due to P, the beam will bend, and fixed end reaction will push back the beam. Push at A, push at B, push back the beam to its original position. Means that by applying the fixed end moment in this direction and in this direction, Okay, the beam will go back to its original position. Fixed end moment, fixed end moment is behavior. Fixed end moment is behavior. Behavior. Okay, to remain straight. To remain straight, the moment must acting in this direction. Okay, to remain straight. This beam, okay, this beam, to remain straight, we have to apply moment in this direction and this direction. Then only it will go back to its original position. Because if we have bent beam like this and we apply FEM in wrong direction means, okay, means that this beam will fail. Dia patah lah. So dia akan jadi macam ni. And dia akan patah. Okay, so yang ni fail. So yang ni behavior, the right behavior. The right behavior. Go back to its original position. Go back to straight position. Okay, that is the reaction definition. Okay, to remain equilibrium. To remain equilibrium. Okay. So in order to analyze, okay, when move to fixed end, okay, it is under fixed end reaction. Fixed end reaction. It is for Q naught or equivalent nodal forces. So what we have to do is we have to analyze separate element. So when we analyze element number one has this 3, 4, 5, 1. This is element number one. And for element number one, the beam is subjected to UDL. So UDL 1 kilonewton per meter, and the length is 9. The length is 9. This is 9 meter. Okay, so 1 kilonewton per meter. So for the fixed end reaction, this is the vertical reaction, and this is WL over 2. Because this is W, this is L, and for the UDL ni dia loading dia macam ni, segi empat tepat. Okay, segi empat tepat, so dia akan jadi P and L, P dengan L. Okay, so bukan, the point load is P kali L. The point load is located at the center, not P. W, it is located at the center. So WL is located at the center. So to distribute it equivalently, so dia akan balance at A and at B. Okay, so the formula is WL over 2, WL over 2. Okay, and for the moment is always acting in this direction compulsory for this load, because it will deflect like this, and we have to apply moment, so that the beam will move back to its original position. Dia nak jadi straight balik, kena apply moment. So this moment formula is WL squared over 12, WL squared over 12. Okay, WL squared over 12, WL squared over 12. Okay. Okay, here I have actually detail out how we get the Q naught. Okay, we have two element, element 1, this is element number 1. Okay, so for each element, to analyze this, for each element to we have to draw two diagram. This one is for element 1, this one is for element 2. Okay, two diagram. For element number 1, okay, this is the formula, okay, this is the formula, and we have to compare with degree of freedom. Compare the upper diagram and the lower diagram, we have to compare. Okay, same goes to diagram for element 2, where we have to sketch two diagram. One diagram representing degree of freedom just for element 2, and another diagram is for the fixed end reaction. This is the formula based on loading. Okay, so what we get here is Q1 naught and Q2 naught. Q1 naught refers to equivalent element nodal force for element 1. Q2 naught is refers to equivalent element nodal forces for element 2. Okay. Fixed end moment ni yang complicated part under beam analysis. Okay, because we have to consider Q naught every time we analyze beam. Okay, this is Q naught again Q naught equivalent nodal forces. Q naught is equal to Q1 naught plus Q2 naught. So what is Q1 naught, what is Q2 naught? It comes from element 1 where it is subjected to UDL, and element 2 where it is subjected to point load. 10, this is 1 kilonewton per meter. Okay, so based on this, we have to balance this. 1 kilonewton per meter. We have to balance. The balancing of this is 1 times 9 meter. We get 4 0.5 and 4.5. This is the balancing. Okay, the balancing equivalent element nodal forces. Okay, we have to balance for the vertical forces. Then we have to balance. This is 5. This is 5. This is for element number 2. Okay, for the UDL, okay, the moment WL squared over 12 equal to WL 6.75. Okay, this is using calculator. This value is 6.75 and 6.75. Okay, and for 3.75. For element number 2, is 3.75. 3.75. Wait. Take some time to sing this. Okay, just wait for a while. Okay, equivalent nodal forces ni dia macam ni. We have to balance the member with load. Okay, for example UDL tu dia point UDL is actually point load that is subjected at the center. Changing the UDL to point load is WL, which is subjected at the center. So that is why 1 times 9, we divide by 2, we get 4.5, 4.5. Because WL is equivalent to P actually. WL is equivalent to P, which is subjected at the center. So the vertical reaction is 4.5 and 4.5 for AB. And for BC, BC is subjected to point load at the center. Point load at the center means to be balancing. It is 5 and 5. 5 and 5 equivalent to 10. 5 and 5 is equivalent to 10. Okay, and not only vertical reaction, fixed end reaction for beam. We have to have the vertical reaction. We also have moment. It is called as fixed end moment. Fixed end moment, we use formula given in appendix. For UDL, it is WL square over 12. WL square over 12 for UDL is 6.75. 6.75. The direction, the moment direction as stated here, representing behavior of the beam. The beam is bent. Okay, and then the moment will push back the beam to its original position. Nak jadi straight balik, kena apply moment in that direction. Okay, so that is why we get 6.75, 6.75 for A and B. Okay, when move to member BC, beside vertical reaction 5 and 5, it also has moment at B and moment at C. And the formula to calculate the moment at B and C due to point load at the center is PL over 8. Okay, so don't worry about the formula because the formula is given. However, the behavior is important. Okay, so the PL over 8 acting this direction, these two direction. Okay, and the value is 3.75, 3.75. We get from PL over 8. Okay. What is Q1 naught? What is Q1 naught? What is Q2 naught? What is Q1 naught? What is Q2 naught? Q1 naught is, okay, four values of Q, four values of Q, and Q2 naught is four values of Q, okay, four values, and the Q1 naught and Q2 naught is also is known as equivalent. So yang dua ni nama dia equivalent element nodal forces. Sebab yang ni for element. So tambah the word element. Equivalent element nodal forces. Equivalent element nodal forces. Okay? Okay. So value kat sini actually we have to there are four values. Sebab kat sini nampak tak ada four value. One, dia ada four values for element 1 and also 4 values for element 2. 4 values for element 2. So we have to put this value in matrix under Q1 naught and Q2 naught. So how we want to transform into Q1 naught and Q2 naught? Okay? How? So we have to label according to, we have to put the value by following the degree of freedom, okay, based on what we have label under K. Means that dekat K tu, kalau dekat K tadi kita label dia sebagai 3, 4, 5, 1. 3, 4, 5, 1. So dekat sini yang ni dia sama dengan K1. Label ni sama, 3, 4, 5, 1. So ambil balik the same label. Okay, 3, 4, 5, 1 and Q2 naught, the label will be 5, 1, 6, 2. Okay, so mana satu value for 3, 4, 5, 1. So that is why tadi ada satu lagi diagram. Okay, yang mana dekat diagram tu ada this label. Okay, this is actually the label that we have used in labeling K1, 3, 4, 5, 1. And this degree of freedom, we have to compare with this. Compare. For example, okay, to be more easier, so let's say I just put label like this. So this is 3, 4, 5, 1. Okay, so by looking at this diagram, what is the value at position 3? What is value for position 3? Okay, this is position 3. This is position 3. This is position 3. So what is the value for position 3? The first value, looking at element number 1, member AB. Member AB, this is A, this is B. Okay, for member AB at position 3, what is the value for 3? What is the value for 4? Okay. What is the value for position number 3? Looking at this diagram only. Value at position number 3. Okay. Value at position number 3. Yes. The value for position number 3 is 4.5. So this is 4.5. 4.5. Okay, we just need to compare the fixed end reaction and the degree of freedom. Okay, continue. Position 4, what is the value? Position 4, what is the value? Position 4, what is the value? Now we move to position 4. What is the value for position 4? Okay, position 3 is 4.5, correct? Position 4.5 belong to 3, yeah? 4.5 belong to 3. Okay, now 4, position 4. Position 4, the value is 6.75. 6.75. This is 6.75. 6.75. Okay, correct. Okay, next. Position 5. Position 5. Position 5. Okay, at position 4, it is positive. Position 4, it is positive. Sebab, ni moment ni dengan yang ni sama direction, same direction. Same positive. Same positive. Okay, 5, it is 4.5. 4.5, 1. Position 1. What is the value for position 1? You have to include negative whenever it is opposite direction. Position 1. Yes, position 1 is negative. 6.75. And in opposite condition, this is, okay, one is clockwise, one is counterclockwise. So value for number 1, value for position 1 is negative. So this is negative 6.75. Okay, there are two parts under beam analysis that you have to focus. Okay, the rest are all same with thrust analysis. Number 1 is how we label the degree of freedom for beam. Okay, number 1, because we will have normally the displacement is is rotation, like what we have done now. Okay, that is the first thing that you have to understand. You have to be careful. Number 2 is when we analyze this equivalent nodal forces. Okay, focus on these two in analyzing beam. The rest are all the same. Okay, so now we move to element number 2. For element number 2, what is the value for position 5? Position 5, what is the value for position 5? Wait. Okay, the degree of freedom, okay, this and this is 5162. 5162. 5162. Okay, so we have position 5 for position 1, position 6, position 2. Okay, now what is the force value at position 5? What is the force value at position 5? It is 5. It is 5. Okay, next. At position 1. At position 1, what is the value? At position 1, what is the value? Position 1. Position 1 refers to moment. It is 3.75. 3.75. Position 6. What is the value for position 6? Position 6. Position 6, what is the value? Position 6, what is the value? It is 5. And last value, position 2. Position 2, what is the value? Position 2. Next is position 2. Position 2, what is the value? Yes, it is negative 3.75. 3.75. Then we have to combine these two Q naught. We have to combine these two Q naught to produce Q naught in 6th position. Q naught in 6th position. So we have to combine to produce Q naught in 6th position. And it must be in order 1, 2, 3, 4, 5, 6. Okay, we have to combine Q1 naught and Q2 naught. We have to combine, and based on degree of freedom, we have label. Okay, so we have to find 6 value of Q naught. So this capital Q naught refers to equivalent nodal forces. Okay, I want to ask everyone now. Okay, give me the value at position 1. Give me the value at position 1. Give me the value at position 1. Position 1. Position 1. This value plus this value. Negative 3. Negative 3. Okay, next value, position 2. Position 2. Position 2. Okay, the first value is negative 3. Okay, position 2. It is negative 6.75 plus 3.75. It is negative 3. Negative 3. Okay, next move to value at position 2. Value at position 2. Negative 3.75. This one. Negative 3.75. Yes. Negative 3.75. Okay, next value. Position 3. Position 3. Position 3. Position 3. Next value. Position number 3. Negative 3.75 is position number 2. What about position number 3? 4.5. Yes, it is 4.5. Position 4. Okay, next value, position 4. Position 4. Position 4. Position 4. Okay, 6.75. Okay, next value, position 5. Now, position 5. 5, 4.5, and 5. Position 5, what is the value? Position 5. Position 5 is 9.5. 9.5. Position 6. Position 6. Position 6. Position 6. 5, yeah? Position 6 is 5. 5. Position 6. Position 6 is 5. Position 6 is 9.5 and 5. Okay. Okay. Okay, this is Q naught. This is Q naught. So this is Q naught. So this Q naught we will put in the stiffness equation. This is the stiffness equation. Okay, stiffness equation. This is Q nodal forces, D nodal displacement, and Q naught equivalent nodal forces plus Q naught. Okay, so write the stiffness equation for the beam. So this is the answer. If the question asks you to write the stiffness equation, so this is the equation. Okay, if it is not asking, okay, actually you can skip this. Yang ni this equation you can skip kalau soalan tak minta. Okay, sebab whenever we want to solve for the unknown displacement, it is just like we analyze unconstrained degree of freedom. So we just need to have these two, this, and this. Okay, so of course in your mind you should be able to have this in mind, because we will solve the unknown reaction also using this equation. But you can also this is not compulsory to write in full. Okay, because when we want to solve for the unknown displacement, okay, we just need to consider this unless support settlement is given. Okay, so solve this. So we get displacement both radian, because d1 remember is theta at B, d2 is theta at C. So that is why d1 and d2 the unit is in radian. So using this d1 and d2, we have to substitute into the stiffness equation. So when we want to calculate Q3, means that this line times with this plus with this. Okay, whenever we want to calculate Q3. Okay, so line number 3 times displacement plus 4.5. Okay, so same goes to Q4. Whenever we want to calculate the value of Q4, so Q4 means line number 4 times with displacement plus 6.75. So this the mathematical process is like this, but I have shortened this into this. Okay, so this 10 kuasa 5. Okay, this is position 1 and position 2. This is position 3, 4, 5, 6. Okay, so the Q naught for position 3, 4, 5, 6. So in order to get the 4 unknown reaction Q3, Q4, Q5 and Q6. So kat sini Q4 belong to moment. So kat sini unit dia moment. So yang ni moment. moment at A. That's why you need the kilonewton per meter. So dah dapat yang ni, kita boleh combine balik. Okay, combine back in the main diagram. Okay, put all the value, okay, that we get, the four unknown reaction, and from that we can draw the shear force diagram. The shear force diagram, okay, UDL, kalau UDL shear force diagram dia incline like this. Sometimes dia jadi two triangular and ada intersection. Sometimes dia hanya jadi trapezium. Okay, so bila ada intersection macam ni, dia akan jadi maximum moment in the bending moment diagram. This intersection means maximum moment in the bending moment diagram. Okay, this is also intersection. So this is the value. Okay, if you get trapezium, okay, for UDL, so means that in the bending moment diagram, okay, it has no maximum moment. It has no maximum moment. Okay, this note I have actually put into your notes, one note, so you can refer to this. Okay. Okay, before we end session, let's look at this this one. Okay, very fast. Okay, just wait for a while. Okay, so procedure will be the same, except we don't have to put coordinate, we don't have to calculate Cx, Cy, because there is no Cx, Cy in the formula. Okay, in the formula there is no Cx, Cy. Okay, there are two things that you have to highlight. Number one is the degree of freedom. Number two is the equivalent nodal forces. Okay, by looking at this beam, okay, if we want to, okay, by looking at this beam, there are two fixed support. Conventionally, okay, it is 3 and 3 conventionally. But since we don't have to count x, we just need to count 2 here, 0 here, 2 here. Means that when we sketch, one for unconstrained, one for constrained, what we get is, okay, we have 1, 2, and 3. 1, 2, and 3. Okay, this is another note, something like this. Okay, we have to put as note. If there is a changes in EI, or if there is a point load, so we have to consider this as note. Okay, so we have 3 notes, 1, 2, 3, 1, 2, 3. So 4 we have to put here, 1, 2, 1, 2. So there are 4, and remaining is 2 here. Total must be 6. It is 3 times 2. 6 DOF. Label, we label as 1, 2, 3, 4, 5, 6. Okay, 1, 2, 3, 4, 5, 6. So when we produce K, we will get K1 and K2. K1 and K2 for beam is 4 by 4 matrix. Is 4 by 4 matrix. In terms of EI, okay, use length, it is 4 by 4, and we will label as this 3, 4, 1, 2, 3, 4, 1, 2. And this is also 3, this is 1, 2, 1, 2, 5, 6, 1, 2, 5, 6. Okay, this label this label we will use also for Q1 node and Q2 node. This label we will use again in Q1 node and Q2 node. Q1 node is 3412 and for Q2 node is 1256. Okay? Okay, to calculate K1 and K2 as usual, we just need to use L, okay, to calculate the value for K1 and K2, and Q1 node and Q2 node is equivalent element nodal forces. Okay, we look at the diagram. Okay, in this case, UDL along member AB and BC has no member load. BC has no member load. AB has UDL, BC has no member load. So we have to assume that AB has both fixed end. We have to assume that. Okay, so for Q1 node, so we have to assume that both end fixed. This is A and B. UDL, the value 9 and 4, the value is 9 kilonewton per meter and 4 meter. Okay, so this beam, okay, we have to analyze it, okay, to calculate fixed end reaction at A and B. Okay, the system must be in equilibrium. So this W we have to times by L acting at the center. 9 kali 4, 36. 9 kali 4, 36 bahagi 2, 18. So we get this as 18, we get this as 18. Okay, WL over 2. For the moment, it always acting in these two direction because of the behavior, and the formula is WL squared over 12. WL squared over 12. WL squared over 12. WL squared over 12 is 12. So this is 12, this is 12. 12. Okay? So, just like what we have done previously, so label this is 3412. 3412. So we have to transform into the matrix. So 3 is 18, 4 is 12, 1 is 18, and 2 is negative 12. Negative 12. And then for element number 2, there is no point load, there is no UDL, so all this will be 0. So this Q1 node and Q2 node we have to combine to produce the structure, the equivalent nodal forces. Okay, so from this, okay, we will have Q. Okay, 6 value of Q. We have D. We have Q naught first. Okay, we have Q naught. 6 value of Q naught. And we have D. 6 value of D. And then we have K. Okay. So all these must be written in order. So this is also 1, 2, 3, 4, 5, 6. This is 1, 2, 3, 4, 5, 6. And based on this, we know that there are displacement, two displacement. Okay, it is D1 and D2. And based on the constraint system, we have 4 unknown reaction: Q3, Q4, Q5, Q6. Okay, and opposite condition, D3 0, D4 0, D5 0, D6 0. Okay, D1 and D2. Okay, in opposite condition, we have Q1 and Q2. Q1 and Q2. Q1 belong to, look at back to the main diagram. We have labeled this as S1 and 2. So Q1 is negative 20, Q2 is 40. Q1 is negative 20 because it is opposite. Q2 is 40 because it is in same direction. So it is negative 20 and 40. Negative 20 and 40. So here is negative 20 and 40. Negative 20 and 40. 3 to 6 remain as symbol. 3, 4, 5, 6. D, D1, D2. Position 3, 0, 4, 5, 6 for the nodal displacement, and for Q naught we will get from Q1 naught and Q2 naught. Q1 naught and Q2 naught. 18, negative 12, negative 12, 18 and 12. 18, negative 12, 3 is 18, 4 is 12, 5 is 0, 0. Then, having this, we just need to combine or transform this into the force displacement equation or stiffness equation. It is force displacement equation or stiffness equation. Okay, it is Q is equal to KD plus Q naught. Okay, so Q we have negative 20, 40, Q3, Q4, Q5, Q6. K in terms of EI, so we calculate K, D1, D2, 0, 0, 0, 0, plus Q naught, 18, 12, negative 12, negative 12, 18, 12, 0, 0. So having this, okay, we complete the stiffness equation and we use this equation to solve for the unknown displacement. Unknown displacement. Okay, so step number 1, we label 1, 2 here. Okay, then we write the stiffness equation K1, K1 and K2 in terms of EI, then We combine to have the structure stiffness matrix. It must be 6 by 6 because of the 6 degree of freedom. And then, okay, we define the nodal displacement and nodal forces. We must look at the information given in the question, and then we produce the equivalent nodal forces using the fixed end reaction formula. Okay, we get this and this. Okay, we get Q1 naught and Q2 naught. Q1 naught and Q2 naught combine to have Q naught yang ni tadi. And after that, we solve for the unknown displacement by only considering unconstrained degree of freedom system. Okay, then we get D1 and D2. D1 and D2, D1 is in vertical component, this is in meter. D2 is in Z component, it is in radian. Substitute into the stiffness equation, then we calculate for unknown reaction. This is for unknown reaction. Okay, so once we get this four unknown reaction, okay, we put back into the diagram. Okay, if the answer is correct, then we can draw the free body with the bending moment diagram, the shear force diagram and bending moment diagram. The diagram must be started at 0 and end at 0. This is the start point. The start point, and this is the last point. Last point. So it is actually start from 0 and end at 0 for both shear force diagram and bending moment diagram. Okay, this is the case where we only have trapezium. This is trapezium. Trapezium means no intersection. No intersection means there is no maximum moment. No maximum moment in the bending moment diagram. Okay, it is just like this. Okay, so these are the two formula. Beam, indeterminate beam, we calculate using stiffness method. The procedure are all the same except two parts. Okay, three. Okay, in the main diagram, we don't have to label coordinate. We don't have to put arrow. Okay, number one, and then we have to label the degree of freedom according to unconstrained and constrained. So we have to label it carefully. Okay, and after that, we have to calculate equivalent nodal forces. Nodal forces. So the idea is the member cannot carry loads. So due to that, we have to distribute to the nodes using the formula given in appendix. Okay, the idea is we have to take out the element and then we assume that both ends are fixed, then we apply the formula. So the idea is we want to make sure that the system is in equilibrium. That is why so every vertical load must be balanced with vertical reaction, and beside that we have to calculate the moment as well. Moment occur at fixed support. Okay, and after that we can solve for displacement and reaction. And normally if the question asking you to draw the shear force diagram and bending moment diagram, we combine back into one diagram and we draw the diagram. Okay, so that is all for this session, beam analysis. Okay, so thank you very much. So inshallah we will continue in the next session. Thank you. So we will meet again inshallah. Okay, Assalamualaikum warahmatullahi wabarakatuh. Okay, thank you all.